Good morning and welcome to this session. My name is Paul Messina from Argonne National Laboratory, and it's my pleasure to introduce the first speaker, Sadasivan Shankar. Sadas is the first Margaret and Will Hurst visiting lecturer in computational science and engineering at the Harvard Paulson School of Engineering and Applied Sciences. And his role there, he's involved in teaching and in research in the areas of large-scale computational methods, chemistry, and materials. Dr. Shankar earned his PhD in chemical engineering and materials science from the University of Minnesota. And he's initiated and led multiple efforts at Intel, where he spent most of his career. Most recently, he initiated the materials design program there. He's co-inventor in several patent filings covering areas in new chemical reactor designs, semiconductor processes, bulk and nanomaterials, device structures, and algorithms. So it's my pleasure to introduce Sadas, who will talk about his concept for a new way of doing co-design, Co-Design 3.0, configurable extreme computing, leveraging Moore's law for real applications. Sadas?
Thank you, Paul. Thank you, Paul, and thanks to the organizers for the invitation to lay out this idea of what co-design is. So I'm going to start with the basic premise of this talk, which is that tera and petascale computing did not translate to proportional orders of magnitude increase in the modeling of physical applications. As a user, so I am a user of computing. I don't design the computers, but as a user, I have been through several of these cycles and these scales. We were one of the biggest consumers of compute cycles at one time, at least in the top 4. And we didn't see that much of turnaround time increase because of newer and newer architectures. The second one, this is attributable to many reasons, software and hardware, and also some of the algorithms. So the basic premise of this talk is I'm going to present enough circumstantial evidence which I think will help us address some of these issues in the co-design. So with that said, let me walk you through a little bit of a background here. So in the materials, I have been involved in looking at all different scales, all the way from atomic scale and quantum scale into going into the entire microprocessor, looking at Joule heating and effects and stresses in very large microprocessors. So that essentially involved metals, insulators, ceramics, semiconductors. So the point is I have been a voracious user of it, and I will also show you the time evolutions of what all computers I have been involved in. This is the one on the left is a picture of me in front of Cray 1 in the late 80s, in which I wrote my thesis on. So we had the biggest Cray 1 and Cray 2 in the Minnesota Supercomputer Center at that time, and we have used that quite a bit, and then later switched to Paragon, in which Paul and Intel were involved in it. Caltech and Intel was involved in it, and then moved to clusters, and now I have been also involved in running applications on one of the larger mainframes. So my outline of talk is essentially 4 aspects. I think I showed you the premise. Can co-design address the 2 aspects that I talked about? Can it leverage things now that it couldn't do in the 80s and 90s and 2000s? And can it solve problems of social relevance in an economically viable way? And then I'm going to walk you through 6 scaling paradigms, 3 in science and engineering, 1 in computational science, and 2 in technology and economical. The reason is this is essentially to look back at history and look at the things happening around us to see what are the lessons we could learn from that. And then can we leverage the 6 paradigms for Co-Design 3.0? I'm not going to have an answer because I don't think there is a unique answer to this question of is there an optimum way of doing co-design, but I will present enough circumstantial evidence to say what would work with a higher probability. Okay. So if I am talking about co-design 3, then I should tell you what is co-design 1 and 2 in the same framework. So let me kind of walk you through that. If you were to assume that all computing and applications can be broken into components, 5 components, they are the hardware platform, the algorithms, software, applications, and architecture. There's no reason to divide them up this way, but this is a good way to divide that, as you will see, because the people working on it and the way they have essentially turned out, different sets of people are involved in it. So this seems like it seems like a reasonable way to divide that. So if you were to look at these 5 as components, the first one is the hardware, the second is the algorithms I mentioned, which includes compute, communicate, data analysis, numerical techniques. Then software means actual software that you could run the algorithms on. That would be middleware, libraries, and apps. And then the applications could be from biology, bioinformatics, chemistry, materials. And the architecture could be von Neumann architecture, or like you saw in Tom's talk before, analog computing, optical interconnects or so. If I look at these as 5 components, and I kind of make them into 5 Lego type blocks, let's say that they are the 5 blocks. Then co-design 1 was something in which happened mainly in the 80s and 90s, I would say, where the architecture, the design, the software, the optimization were all done serially. The application people came to kind of appreciate what was needed after all of them have happened. So this was done very serially. The architecture would be picked up first, then the hardware would be put together, and then the algorithms would be optimized for that given hardware, and there would be no feedback which changes the architecture. So this is what I would call the co-design 1. Now I would say we are a little bit in co-design 2.0 and a variation of that, in which there is a higher level of concurrency between them. They are not all being done at the same time, but they are essentially being done more or less with overlaps between them. The exascale computing project is one in which it is trying to increase the concurrency between them. Okay, so now I'm going to walk you through the 5 different scalings and try to make a case of where the co-design 3 ought to be. Now that I have told you what are the co-designs 1 and 2 are. So let's start with scaling of things, where natural and synthesized things span several orders of magnitude. So the scale of things is essentially talking about the scale of things that we are trying to address. So I will start the first one with the Department of Energy slide, actually. On the left side these are the scales in nature. If you look at the scales, they are essentially by 10 to 15 orders of magnitude from bottom to the top. The bottom is at the atomic scale and DNA, and then at the top are where organisms are. Now let's look at the synthesized scale. They also span the same spectrum. You have essentially single dots at the bottom, atomic transistors and single electron transistors, and as you go up, you kind of have more and more put together systems. So essentially you are again spanning the same order of magnitude. Now if you were to look at the time scales, this is the natural time scales. If it's not clear, it's microsecond on the left-hand side and essentially in order of 2 weeks on the right-hand side. So they essentially span like 12 orders of magnitude time scale. On the left side, you have the enzyme turnover time and the electron transfer reaction time. On the right-hand side is the actual cell's lifespan. So that essentially spans about 12 orders of magnitude again. If you look at the man-made time scales, this is synthesis of a film, a chemical film. If you look at it, the surface reactions are 10 to the power minus 10 to 10 to the power minus 1 seconds. So that essentially again has about 9 orders of magnitude. But if you were to look at the slowest process, which is transport and diffusion, again you have about 11 orders of magnitude. So it's safe to say that between 11 and 12 orders of length scales and time scales exist. So that is the scale of things. Now I'm going to show you combinatorial scaling of the kind of real problems are. If you look in the 80s, the electronics industry, essentially we are looking at about a dozen elements in the periodic table. And if you were to fast forward to 2000s, this is how the periodic table essentially looked like. So you were essentially looking at about 70 elements if they are non-toxic and non-radioactive and some other constraints, stability of the element. Now, if you look into the aerospace industry, this is the early alloy that was used in aircraft structures. And if you look at now, that has essentially, this is an aluminum 319 alloy, and which essentially also has increased the number of elements that you look at. There's an order of magnitude. Now, if you look at energy, from the 1700s to where the 2000 is, the number of elements that essentially go on, the energy has also increased like an order of magnitude. So most of them have increased by an order of magnitude in terms of the number of elements. But remember, this is about combinatorial scaling. The materials are not the elements. There are about 70 usable elements in the periodic table, and you kind of tap it off there. But multiple materials are needed to make any useful device. For example, a transistor at 45 nanometer has 9 elements in it, even though it's only supposed to be 45 nanometers. Okay? And these elements are typically alloyed. You have 4 components of that. And you can see even a 4-element combination will give you about 24 million possibilities. And there are multiple steric ways of combining. So if you put all these together in a figure, on the left-hand side, if you take the 70 elements in periodic table, you alloy them and compound them, you get of the order of millions of combinations. Now there are, for inorganic single crystalline materials, there are of the order of 100,000 crystal structures available. Now if you make an interface, if you cleave them and put an interface, you are of the order of hundreds of billion. And if you put together the multi-component system with multiple interfaces, you are in trillion combinations. So even though the number of elements you started off with 70, you could potentially have trillion combinations of the eventual system in order to bridge it from an atom to a system. So that is the combinatorial part of it. Now, if you look into the organic, but one point I wanted to make is not all these really happen because of thermodynamics and chemical kinetics. Not all of them are kinetically feasible. Now, if you go to combinatorial scaling for the organic systems, what you have on the x-axis are the number of molecules. The y-axis is the number of substituents you could put onto that molecule. The table on the left-hand side is showing how many have been really detected and found. So in principle, even by going up to 3 power 10 to the power 6 molecules, you could have about 3 10 to the power 6 substituents. But if you look at the last row, there's only one such molecule has been found in nature, which means that they are possible and they have not been detected yet. So if you were to draw the same plot as I showed you on the inorganic materials, you can essentially have commercially available, there are of the order of million chemicals, but if you put 50 substituents and non-organic molecules, you can potentially end up with 10 to the power 30 combinations. So organic obviously is much more bigger than inorganic. And the highest reported value in literature is 10 to the power 60, another 30 orders of magnitude higher. So the combinatorial thing would make it very hard for design of a practical application. Now let's look at the scaling of the applications itself. If you were to look at data, digital information that is essentially kind of running most of the internet, The data usage has increased by a nested power law, the power law of number of computers, the power law of number of microprocessors, the power of number of interconnected computers, and so on. And that essentially is now of the order of zeta scales of bits. So if you look at a real application now on the internet, no matter how you slice it, the order of data that you have is of the order of zettabytes. That is 3 orders of magnitude higher than even the exabyte. Now, if you were to, so we are talking about real applications, and this is essentially trying to plot on the x-axis length scale, the y-axis the time scale to simulate something. So if you were to go from the bottom to the top, you essentially, if you used quantum mechanics, you are stuck at very small length scales and very small time scales. If you were to design a big system at the design level, then you have to use some other abstracted model. So from an application perspective, you still cannot use atomic scale accuracy all the way to the system. If you look at the biological application, you have a similar kind of a thing. The x-axis is again the length scale and y-axis is again the time scale. On the bottom is again quantum, but this is taken from a different publication. And if you were to look at it, you essentially have at the membrane level, if you want to simulate, you still have that kind of a complexity. So the point of this is the applications are more at the very high end of what could be simulated or what could be modeled on the computer. With any amount of computing, this cannot be bridged. So now I am going to show you scaling of algorithms. So remember, we had divvied up software, hardware, algorithms, and so on. But the algorithms are the way in which you actually compute something. So I'm going to show you the computability of the algorithm. When you take small materials, people generally tend to say, oh, the materials are smaller. You could essentially do quantum simulations all the way through. In reality, it doesn't happen for various reasons. One of which is, even if your single material is small, there are a lot of interface effects. Because of that, you essentially have what is called what I call as a proximity effect, which means that atoms can see things 50 to 60 nanometers out. So it's not at the angstrom level. There is some kind of a non-local effect that even if you go with smaller materials, you will actually see that. And that you can see on the DNA as well. You have 3 billion base pairs, but the protein folding time goes from micro to millisecond. So on the algorithms, I took from a very recent publication to make my point of where the co-design. So this is essentially giving us a hint of what it is. So let me tell you what they have plotted. On the x-axis is just the chronology of the years. The y-axis is the accessory time scale, how much you can actually simulate it. The blue line is more like the Moore's law, the traditional Moore's law. The red line is the molecular dynamics. So what I did was I essentially took that and tried to calculate how many doublings happened between 1975 and 2010 from this graph, just to give you an estimate. And if you look at that, there is about 18 doublings, which is the equivalent of saying the Moore's law. Essentially, there have been 18 doublings. And this actual time of doublings have many reasons why it is 18, not exactly every 2 years. But let's just assume that the 18 years hold. But if I look at a molecular dynamics accessibility time, which is the red curve, they essentially doubled about 20 times in the same time. So if I subtract one from the other, because these are logarithmic power laws, I would say that the algorithm efficiency doubled only 2.5 times by itself without the Moore's law. And this point is a big hint of where the solution is, and I will come back to this graph again as I make the final case, but this essentially shows you that. Now, if you look in the same about 15 years in molecular dynamics capabilities, there's a reason why the algorithms are not scaling. It's not that people were not coding efficiently. the complexity of the potential, interatomic potential that was being used in 15 years have become more and more complex and more realistic. So people are trying to solve more real problems. And that is what I wanted to show you, that in 15 doublings of computer power, 50 new potential formalisms have happened. So people tend to solve more realistic problems than toy problems. Now, if you were to look forward, if you look at an atomically assembled device that my team did on the computer, so this is actually an entire transistor. This was published in 2011. It has an order of million atoms. And so can you simulate it? You can assemble it, but can you actually simulate it? And that's what I'm going to show you why not. If you look at the time scale here, on the x-axis you have time in seconds. The y-axis are the flops, just linear interpolation. So this is very simplistic calculation. We can do, back when this plot was done, we could essentially simulate of the order of megaflops. If I really want to solve a problem, remember about the time scales that I showed you early on in the scaling of the actual things. You need to go to the order of an hour, which means there ought to be a time scale up of 10 to the power 5 to 10 to the power 6 needed, assuming that the algorithm scales linearly. We know that no algorithm scales linearly. If you look at algorithms that don't scale linearly, you have atoms here, but this time it is not length scale, it is not time scale, it's length scale. If you look at the quantum scaling, which is like n cubed, you can see that even with exaflops, you will not be able to solve the real problem that you want to solve, because the algorithm scaling goes n cubed. And if the computer scale, the computational power scales lower, then you cannot actually get to the problem you want to solve. And why is that? There's a lot of reasons to it, and I'm going to end this scaling part showing how the chemistry scaling works. These are, on the x-axis, the number of electrons or the number of atoms, depending on what you look at. The y-axis is the transferability or accuracy. The left-hand side is the most accurate quantum chemistry codes. The right-hand side is, as you actually increase in size, you will not be able to solve, the cost becomes so prohibitive that the so-called coupled cluster type simulations, you will not be able to solve with the accuracy that you need. Because some of them scale like n to the power 7. Remember, this is the scaling of the algorithm. So the least accurate scales like n squared or linear. Most of the quantum codes scale like n cubed. The more accurate ones scale n to the power 7. So the algorithms scale very, very non-linearly as a power law. So now I will kind of come to the technology scaling, because this is about Moore's law after all. If you look at the Moore's law plot, this is 40 years of microprocessor trend data taken from the paper from Mark Horowitz. You can see that the transistors have scaled where they are now. This is more like a 2012, 2013. I think this data was collected up to 2010. So you can actually see that the spec thread performance, the frequency, the power, and the logical scores all are scaling, but with different scale laws. So this is about Moore's law. We are getting a lot of transistors, but the memory itself is essentially scaling less optimally than the CPU speed. The DRAM speeds essentially have scaled about 2 to 11%, while the CPU speeds have increased 25 to 20%. Now, if you look at chip area and power consumptions, this is taken from a publication from Intel. You can essentially see that the leakage power is starting to increase very highly, which is one of the reasons why you cannot use the transistors as much as you want. Now, remember I showed you the Moore's law, but there are hidden gotchas in that. There are 3 of them which are flattening out quite a bit. Sorry, I didn't mean to jump, power, frequency, and single thread performance are flattening out, which means they are not scaling like the transistors. So that gives you a hint that there is something that is not optimal. And then the bandwidth, if you look at that, the Moore's law computer power has gone up 60%, 100x. The internet bandwidth is essentially going only 57x. So even though the Moore's law is going on, there are other things around which are going at different scales. While the algorithms and the applications we need are scaling much higher. So the needs are very high, but the rest of the collateral and the ecosystem is not scaling as the transistors are. So I just am rewriting Moore's law here. It's the same thing. I took his quote. With unit cost falling as the number of components rise, by 1975, Gordon Moore observed that 65,000 components on a single silicon chip, and that came to be called as Moore's law. So many people talk about end of Moore's law, and people get this part a little bit muddied, because the end is not going to be determined by physics and chemistry, as people tend to think. It's quantum, and hence that's what limits it. But it's actually going to be limited by something else. And it is when the cost of added information processing do not translate to added functionality at commensurate price. So let me repeat that again. The Moore's law limitation is when the cost of adding extra information processing does not translate to an added functionality at the price in which user is willing to pay for. That is when the law breaks down, not when the transistor gets too small, because the smallest information processing unit we know is an electron. So in principle, you can scale all the way to a single electron on 2 states. But the fact is the rest of it, can you keep the cost down integrating all of that into a single chip, is probably what is going to limit it. And this essentially gets overlooked. In order to make the point, I just am highlighting those 3. So added information processing, added functionality, and economics of this addition. And that's the key. So how is the Moore's law going to be limited? It is going to be limited by design, manufacturing, and energy, not as much by physics and chemistry. So, just restating what I said, information processing and functionality are limited by process, control, and the binary unit of information processing, which is typically transistors that on-off, which essentially works electrostatically. The integration of components and the use of the added components by the end user. These 3 is essentially what drives the Moore's law, not just the first item alone. So I think this message becomes much more vivid by the next plot I'm going to show you. This is work that is done by Microsoft in 2011 on an international symposium on computer architecture. The x-axis is the technology node. So you are essentially going, as you are advancing, you are going into smaller and smaller node. The y-axis is the percentage of dark silicon, that the quantity of silicon sitting idle when you essentially have that. Okay? So this is the amount of silicon that essentially is sitting idly when the microprocessor is on. If you look at that, it essentially says that if you look at the CPU, which is the yellow, in which the dark silicon is smaller, which means there's more usage of the silicon. If you look at the GPU, it is getting closer to 100. So the real Moore's law you see is the Moore's law multiplied by this 0.75 or whatever that number is. And if you look at some of it, when the technology scales, it could be 0.05, which means 95% is dark silicon according to this extrapolation. And that may be a little bit of an over prediction, but the point is that at least 50%, if you're not using it, then when you double the transistors, do you actually use them is the question. And then on the cost factor, because as I want to set up for the next scaling, the basic success model in the electronics industry has been a single type of transistor, CMOS type, with electronic switching. There's a global clock and synchronous state for deterministic computing, and then the geometrical scaling, just make it smaller and smaller geometrically. Because it is small, the so-called Dennard type scaling, everything will happen faster because they have to happen through smaller devices. That is the basic success model that has delivered 50 years of this power. However, in reality, as you saw, not all transistors are available, and they are not being utilized for a variety of reasons. So that is where you see the curve flattening. This comes down not just to dark silicon, but also the other things which I showed you, the memory, the latency, the bandwidth, all of that as well. So they are all essentially causing for this flattening. So then the last one, which scaling, is the scaling of costs. That if you look at the ecosystem today, all the problems are being converted into data problems. For example, you have about 6.4 billion sensors. There are about 3.6 billion computers that are estimated, and about 49 billion web pages that are essentially available. In 2020, the estimate is there will be 20 billions of sensors, 7 billion computers, and the estimate for web pages I couldn't see. So because it's all big data, essentially correlation is a strong proxy for causation. So the cause is not that important as long as you get the right correlation. So that's what this data problems essentially help you do that. So remember, this is about economics, this particular scaling. The MapReduce, which is essentially the algorithm framework that is used for a lot of data application, is an open source, and cloud deployment scaling is essentially helping people use multiple applications. Now, everything is big data. The informatics from social networking and personalization is driving it. And I'm going to show you two specific examples here. The MapReduce, if you look at it from 2002 time frame to now, lot of applications are deployed on top of the MapReduce. And you essentially have software which is available free for developers kit that you could essentially use. So this is what the cost is essentially down. So how is that changing it? If you look at the total Amazon Elastic MapReduce clusters launched by customers, they have started their own power law now. Pfizer, New York University School of Medicine, National Taiwan University, JPL are all running applications on the cloud in Amazon. Not just this, but Amazon Web Services have built a special version of the cloud for even the US Central Intelligence Agency under a 10-year, $660 million contract. So the cost is essentially really kind of flattened and distributed across a very heavy user base, unlike the more traditional HPC is doing. So we talked through 6 scalings. So this is to make a case of what the co-design 3.0 is. So now we will look at something else to see what could be happening using these 6 scalings that I showed you, which is essentially an organic fragmentation is essentially happening depending on who the user is. One of the first example is use of field programmable gate arrays. I think all of you know this. The FPGA is an integrated circuit designed. It could be designed by the customer and configured on the field. And it is being used for digital signal processing, medical imaging, computer vision, and many more. The most important application which I wanted to show you is this Anton 2. This is put together by D. Shaw's research. exclusively for their applications in biological, for a single application, molecular dynamics of proteins. The specialized hardware pipelines, they have essentially designed the hardware for a single application, and the software was essentially developed on that. Okay? Now remember this figure, which I showed you before. The Moore's law scales, we said about 17.6 doublings. Moore's law on molecular dynamics scales about 20. So the algorithmic scaling was just 2.3. You remember this. If you look at the topmost point, the red point, that was done on Anton. Now if I include that, the algorithmic efficiency has doubled 8 times instead of the 2.5 times I showed you before. Before, the MD was running on a hardware, but when the MD and the hardware were designed, co-designed, you are essentially getting like 8 doublings. So that is giving you a hint of where it is. But this is not the only thing. This came out in Wired a couple of months back. A special purpose supercomputer from Microsoft, designing computers, essentially a combination of CPUs and GPUs. They call it the Catapult. They are using alternative silicon to execute their neural network models. And Microsoft is not the only thing. This Big Sur artificial intelligence is Facebook, which have their own supercomputer co-designed, where systems to recognize speech, understand the content of video and images, and translate the content from one language to other. Okay? So then what should co-design 3 be? So if I were to sum it up, I would say the co-design would be optimal if it could address problems of societal significance in addition to social networking. Materials would be energy, clean water, health, transportation, and communication. With the following attributes: accelerate time to the product for the end user, and it should be economical. And it should essentially subject to the 6 scaling paradigms I walked you through: scale of things, scaling of numbers, scaling of applications, algorithmic scaling, scaling of technology, and scaling of cost. So it should be low cost. It should be able to use the scaling of technology as we have it, not as we would like it. The algorithms should be co-designed, as I showed you an example. And the applications then would be real applications in protein folding or something similar in materials, a new battery or so. Scaling of numbers is what makes the problem real application harder than what you could do with social networking type problems, because these are driven by physical sciences, not social sciences. So how would this be? Remember the 5 components I showed you? If they could be put together for each application differently at the user level, then we can essentially get much more maximum scaling efficiency from that. And for an example of that, if you take the von Neumann architecture and if you target it to certain digital applications, while you take the neuromorphic computing and essentially make it for pattern recognition. So each application should drive the entire computing hardware platform, the architecture, software development, and so on. So how would this be? So if we were to take the same 5 blocks, each of them may need a different combination to get the most optimum performance of, and then you would essentially fragment it like this. You will put it together differently, a customized technological solutions for customized computing at cost. Cost is important because it is being undercut by a lot of deployment on the cloud and open source. So the core design 3 attributes should be, it should be adaptable, configurable, scalable and economical, and multifunctional. And then the way to do that is by functional diversification on the building blocks level. And there's a lot more I could say about it, but I would like to probably use this to wrap it up.
Thank you very much, Sadas. So I checked the online questions and I didn't see any. There's still time to submit any that way. Are there any questions from the audience in person as opposed to the web?
Mike Norman, STSC. Thank you for a fascinating talk. So do I take it then that FPGAs play a fundamental role in computer architectures going forward?
So that will happen, and it's now beyond the control of any one company or any one user. But just like the FPGA emerged from the more traditional thing, I think that we can go beyond FPGA. I mean, FPGA will be an integral part of it. The more traditional microprocessor would also be part of it. But the final solution would be very different for you depending on what your application is. If it is all big data, a GPU, people would argue, because it's all multi-input, multi-data stream, then you could do it massively parallelization. As I tried to show you, if this were that easily parallelizable, why weren't the molecular dynamics simulations not leveraging an existing architecture? Of the options we have today, FPGA is probably the most configurable option. So I would say it has a leg up on that. But who knows what would happen another 5 years out? So the core design 3.0, as Paul knows, we have been talking to put together something of an entity which has the academic institutions, the Department of Energy, and the private companies to have a so-called marketplace where you kind of test and see what is the right adaptable application. And each application is very different. I showed you MD, and if I showed you for Monte Carlo, it would be very different than data analytics, which would be different. Right now, we tend to take for granted the off-the-shelf components and say that is all we will use. But I am saying, no, let's be more adaptable, but let's do it at cost. So it should not be such an exotic architecture like a very high-end sports car that only a few can buy. It should be adaptable to this marketplace. Otherwise, Amazon will probably be, everybody would be running on Amazon, right? Which may not be a bad thing if you're working for Amazon.
Any other questions? Let's thank Sadas again.